Running these generative AI algorithms at scale can be very challenging, overwhelming, and costly. In fact, there's 3 areas that I want to highlight where there's exponential growth occurring over time. And if I were to log scale this here, then it would look much like this here. But the first one would be the model size. So at the beginning, these models, they were thousands of parameters. Then they moved to millions, and now billions and even trillions. But this requires specialized hardware in order to even run and train these very large algorithms. Now, the second one would be data size. Now, the data size is growing. If you think about Granite and you think about Llama, but a human, in turn, can read about 1 million different words every single year. Now, a system, such as an algorithm like this, can read about 1 billion times 10 to the 6 or 6 orders of magnitude more in just a single month. We're actually beginning to run out of data. By 2030, I think that we're going to see synthetic data actually overtake real-world data. Now, the third one is demand. So over time, you have seen that these models have become integral to our daily lives, right? So when you look at ChatGPT in just 5 days after it was released, it had 1 million users. And if you look about a year later, there were about 100 million users. So every time we think about having to write, a piece, but we can solve this, what's called a white space problem, by using these models to help prompt us or to tell us what we should think about and how we should write. But now if I take these and I multiply them together, well, this gives us this unfathomable compute scale that we need in order to run them, right? And again, this is a log scale here. Now, what this means is that we need this agentic architecture to run these specialized models and to help solve the problem of trying to make these more usable. So what can we really do to help, right, to make this more manageable and usable systems for inference and so on? Well, let's go ahead and find out next. Generative AI algorithms could be scaled across hundreds of GPUs. In fact, you can put them on V100s, A100s, or even look at the different H series that NVIDIA provides, or even other vendors. But even so, with hundreds of thousands of different types of requests per second, this can strain the system, but it could also strain the underlying hardware. So to help out, let's look at a couple of strategies that we can take. Now, the first one is called a batch-based generative AI system. Now here, what happens is we want to create these very dynamic fill-in-the-blank sentences that come from the output of these large language models. We then store them on a content delivery network, and this is really cached all around the world. And then on the edge, we will then pull in all of those fill-in-the-blank sentences, and we'll insert the personalized information and then serve it over to the user. So this becomes a very personalized experience. Now, the second one is cache-based generative AI. Now here, the whole strategy is that we want to cache as much content as we possibly can on servers that are around the world on a CDN. And what we do is we want to find the most common cases that we can generate content for and then push that up. And that means that the least type of content that we generate, we want to do that on demand and then in turn serve it. But this gives us kind of the best of both worlds, where we can cut in half, maybe 90% of the requests per second, and then the other 10% is created on demand. Now, the other approach would be what's called an agentic architecture. And this type of architecture, it's emerging, but it's where you take these very large, complex models and you break them down into smaller models so that they're specialized. So it's almost like a mixture of experts. And these agents, in turn, can communicate to each other. One example would be having a large language model judge the output of another large language model. You could even have another large language model be self-introspective and then pass the output off onto another specialized model that could transform that information that's then in turn served up. But these smaller models then require smaller footprints that then can run and be scaled across these hundreds of different types of GPUs. Now, these types of models, they may not run on these commodity machines or any of the available GPUs that you might have for your team, such as a 32 gigabyte GPU chip. Now, some of them can. There are some Granite models that are smaller, even some Llama models that could fit, and other vendors also have pieces, but the vast majority of some of the most powerful models you need to get to run in other types of hardware. Now, to combat some of this, one of the options is a technique that's called model distillation. But the whole idea around this is that we want to be able to extract the information that really matters to the domain of which we're working on. We can take that information and we can do in-context learning, but traditionally you would want to teach another smaller model through gradient update, so it becomes much more powerful and fine-tuned and can be applied to your problem in a very accurate way. Now, the second method that we could do is called a student-teacher approach. And here, instead of looking at the data per se, we want to create what's called a new behavior. And we can create a new skill or a composite skill based on the task that we want to have. It could be text extraction, it could be summarization, it could be just fluent writing. But having a model that's the teacher that would know some of the tasks, and you could even have a bank of models where your teacher models would then be asked questions by your student models, so the data would flow this way, and then the output from your teacher models will go back to the student so that it could learn over time and develop those types of skills that it would need. And now if I want to look at another approach where I want to shrink a model, quantization is a nice approach. So here is where I want to compress a model into a much smaller footprint. So I would take these 32-bit floating point numbers and I want to make them much smaller. So I might want to make it into an 8-bit representation of that floating point number, or I could do a 4-bit representation. Now, there are different pros and cons of the order in which you do it. So one of them could be you shrink it before training. Now, this requires more compute resources when you do train, but it creates a smaller model, and it still can maintain a lot of the accuracy levels, whichever way you measure accuracy, whenever you apply that at inference time. Now, you could also do this post-training. Now, this is lesser requirements on compute when you train, but when you do and apply this at inference, your accuracy might go down, right? So those trade-offs, right, is something that you do need to keep in mind as you apply this compression technique. If you like this video and want to see more like it, please like and subscribe. If you have any questions or want to share your thoughts about this topic, please leave a comment below.